And I've picked two extremely simple and also, I find, pretty exciting examples from the very recent past. So if you look through the annals of Icpeac and through the periodic table, there's probably one atom which has received in full right the most attention of our community, and that's the helium atom. The reason is that this is a showcase for electron correlation. It's a showcase for calculating electron correlation on ground state energies, for calculating electron correlation in ion atom collisions, for calculating electron correlations in laser atom and synchrotron atom collisions. So this is also reflected in this week's program. For example, there's some news about one photon ejecting 2 electrons, and you will hear about that from Markus Schöffler on Monday. But helium is a very interesting few-body system, not only if you break it apart, it also has fascinating quantum features as you put many helium atoms together, and all of you know that superfluidity exists only in helium. So helium is really a showcase for quantum mechanics. And you heard this morning already in the talk of Jan-Michael Rost about droplets, how you can ignite them and induce all kind of interesting dynamics in droplets, and you will hear a plenary lecture by Paul Scheier about matter included in helium droplets. Now, what's in between? What's in between the single atom and the superfluid helium? Well, if you go from the atom, you can first put 2 atoms together, then you get something which is called the helium dimer. You may think of that as a molecule. It's bound not by a covalent bond, but just very weakly by the van der Waals interaction. And then you can add another atom, and you end up at the helium trimer. And you also will hear during the week a talk from Amin Qasimi, for example, where he shot fast ions onto dimers, looking for very interesting effects there. So for the remainder of this talk, I will concentrate on these 2 species, on the helium dimer and the helium trimer. These are fascinating quantum objects in many senses. They are halo states. I will tell you what halo states are, and they give rise to many interesting features. So there is in particular one question I will try to answer with you. And that is, if you have a few-body system, like 2 atoms bound together, or 3 atoms, by a short-range potential. A short-range potential like the van der Waals force, but the same would also hold for nuclei which you, by the nuclear force, bind together. Now the question I will answer is, what happens to the wave function of this few-body system if you decrease the bond? If you make that bond here weaker and weaker, and in that limit that the binding energy of the system goes to 0, what happens to the wave function? And I will show you what these wave functions are. For 3 particles, that question was first asked, or it was asked much earlier, but it was first answered by Vitaly Efimov, and I can't resist to show you a quotation from Joe Masek on this, because Joe is not only well known for great physics, he's also well known for putting physics in beautiful words. So here's a quotation from him on what is so interesting in this transition right before a bond breaks at 0. And just to quote Joe, in this overview paper, review paper, he mentioned that the great triumph of quantum mechanics was to explain how aggregates are formed. And in this transition region, where a bond disappears, actually a new form of quantum matter arises. And he said that, well, at that transition, we now have to add a third way of how quantum mechanics creates stable aggregates, and that is the Efimov states, which I will talk about at the end of this presentation. Okay, so that's the question. We want to see the wave function in that limit that the bond disappears. So my first duty is to explain to you how we can image a wave function and then try to use these experimental tools to look into these quantum wave function of helium dimers and trimers. And finally, also to Efimov states. So the first, here's an outline. The first thing is experimentally, how do we do that? Then what is special about 2 helium atoms, what is special about 3 helium atoms, and finally, what is an Efimov state and what does an image of an Efimov state look like? So here's the tool. The experimental tool to see a wave function, a molecular wave function, is very old. It's called Coulomb explosion imaging, and the idea is very simple. You take your molecule, you ignite it, make it fly apart, and you do that by charging it up. And then you collect all the fragments here and hope that you can put all the pieces together. And by that, by collecting the fragments after the explosion, you learn how it was before the explosion. Now, how do you ignite a molecule? That's actually conceptually simple. You remove the electrons, and you have charged particles which repel each other. And that repulsion is, if it's highly charged, is simple enough because the potential is 1 over r or 2 over r between the individual particles. And so you can calculate back, and by measuring these endpoints, you can calculate back where they came from. That's the idea. And the idea is really old. It came from the collision community. It was first done with fast molecular beams, which were actually shot through a foil. And that was the first paper where this was done. So here's an outline, and it's still done. That's a recent science paper from 2 years ago. So you take your molecule, you accelerate it by an accelerator, you pass it through a very thin foil, and the only thing which the thin foil does, it strips off the electrons. The heavy particles keep flying, but they are then, since the binding electrons are gone, they are driven apart by the Coulomb repulsion, and eventually they are detected. And this explosion from here to your detector you can calculate, and from that you get the structure. So that has been done in ion accelerators for a long time. I will not talk about that during my talk, but that was the beginning of that technique. Another way to do it, you can pass a highly charged or a very fast highly charged ion by a molecule. So what will happen? Either the high fast charge rips off many electrons to the continuum, or if the charge is slow enough, it sucks the electrons out of your molecule, collects it all, and takes it with it, and you are left with a highly charged molecular ion, which is driven apart. That also has been done for several years. You can do the same thing at synchrotrons. At synchrotrons, if you take a high-energy photon, you take off an electron from an inner shell, an Auger cascade will set in, the molecule by itself spits off many more electrons, and eventually it's highly charged, driven apart. You can image the explosion, and also this has been done in this community for a long time. The last 2 things you can do, you can shine a femtosecond laser onto your molecule. If you crank up the intensity, the femtosecond laser will peel off electrons from the most loosely bound electrons from the outer orbitals. And if the pulse is strong enough and short enough that the nuclei don't move during the talk, during this pulse, then the molecule, after the laser pulse is gone, will explode, and you can image the fragments. And you can do the same thing also with a free electron laser, where instead of sucking off gently by tunnel ionization as you do it with a laser, here you do it with many single photons. And the examples I will show you were experimentally done, even though the details don't matter how it was done, by a femtosecond 800 nanometer laser or a free electron laser, single photon processes. But the idea of all of this Coulomb explosion imaging is that the tools, how you remove the electrons, don't play a role, which is an approximation, but okay. So if you do it with the synchrotron or free electron laser or laser pulse, then your molecules are at rest in the laboratory, and you can place your detectors around it. And how we do that, and how many groups in the world do that, is by creating your molecules in the gas phase in a beam which goes up here. So in here you are your individual molecules. Don't think of this as being a thick gas, but actually individual molecules flying up. You fire your laser or your synchrotron at it. You superimpose an electric field. So these rings here are connected by resistors, and you have an electric field which sucks the positively charged ions towards the position-sensitive detector here, and it also collects the electrons here. For the remainder of the talk, I will not talk about the electrons, just at the ions here. Then you measure where do the ions hit, and what time did it take from here to here, and from this three information, time of flight, 2 positions of impact, for each of the individual fragments of the molecule, you can calculate the starting position and you can put your molecule back together. That's the idea. And to convince you that it actually works, I show you 2 recent examples. The first one is one of the most simple chiral molecules. So that's a methane derivative. In the center is a carbon, and then there is a hydrogen, a chlorine, a bromine, and a fluorine. And these 4 ligands at your carbon you can arrange either in a left-handed or a right-handed geometry. So there are 2 enantiomers which have, besides the small effects of the weak interaction, they have exactly the same binding energy but different geometry, and you cannot go from here to here without a mirror operation. So that are called enantiomers. If you create this molecule in your chemistry laboratory, you get a 50-50 mixture because the energetics is exactly the same for these molecules. If your body does this, your body could, in principle, have this DNA and this, but it doesn't. In your body, it's very selective. You only have one of the enantiomers, and that's what nature does by chemistry tricks, not by energetics. And that is very important in the pharmaceutical industry today. For example, all drugs, or many of the drugs are enantiosensitive, and that's the most famous example, which is Contergan, where one of the enantiomers is actually a sleeping drug, and the other one causes birth defects. So today, that's a big issue to be able to distinguish this from this for all kinds of drugs. So experimentally, we take this racemic mixture, so a 50-50 mixture from the chemistry lab, put it in here, make a very dilute beam, fire a femtosecond laser, some 2 times 10 to the 15 watts per square centimeter, onto this poor molecule, ionize it, and it flies apart. And the guy who did it, you can see here, that's Martin Pitzer. And now I show you what he got to convince you that this technique works. That's a picture from the chemistry textbook. And these points are indeed measurements from this Coulomb explosion by a laser. So you see indeed that the particles fly more or less along the bonds. And you can see there are bromine particles, fluorine, chlorine, and in the back is the hydrogen. And you also see the carbon, which you can't see in this plot. It's behind that. So you see the 3D geometrical structure from it. So Coulomb explosion does show you 3D structure, and it crashed. It allows you to distinguish molecule for molecule which of the enantiomers you had. Let's try that again. So this is from a racemic mixture. We had a 50-50 mixture, and molecule for molecule, we could sort it into one or the other handedness, and by this also see the absolute handedness of this molecule. So that is in 3D, but that's not really a wave function. It's kind of the structure of the system. I promised you wave functions. So how do you measure a wave function? And that is easiest explained at the most simple molecule there is, the H2+. So if you have a diatomic, then it's straightforward. For a diatomic, that's the quantity you want. If you rip off the electrons, you have your 2 charged particles, let's say 2 protons, sitting at an internuclear distance r, which you want to measure in a single-shot measurement. Now, if you remove the electrons, then the potential energy in this thing is 1 over the distance. So you have a potential energy when the electrons are gone, and then they fly apart, and that potential energy is transformed into kinetic energy, which eventually you measure. So the KER, kinetic energy after the explosion you measure, and that is, in classical mechanics, related to the internuclear distance at the instant when you remove the electrons. So that's the idea, and by that you should be able to sample that wave function. So here is a pictorial of this. You start from your wave function in the ground state, that's the internuclear distance. You remove the electrons, which means you go up here. Then your molecule is on this repulsive curve, which in this case is trivial. It's proton-proton, 1 over r. And you go here, and you get an energy because it rolls down that hill here, and this energy is what you measure, and you can work back to internuclear distance. That's classical mechanics. Is that true? Well, never forget about the Heisenberg's uncertainty principle, because that governs what happens actually here. So this is an approximation that you can work your way back from here to here, and it rests on 2 assumptions. The first is that you cannot beat Heisenberg here, and that manifests itself in the point that this wave function is not only a spatial distribution, but it also has, at the same time, a momentum distribution. So these particles do not start in classical words with 0 momentum, but they start with a distribution of momenta, and that, within the uncertainty principle, wipes out the one-to-one mapping, so that at the end you are in accordance with quantum mechanics. But there is a quantum version of that Coulomb explosion, and that's shown here. If you go up here, instead of doing that rolling down the hill classically, you can project onto these wave functions, which are the solutions, or asymptotically it's plane waves, and in here it's just Coulomb waves. So you project onto this wave function and expand the ground state wave function into the eigenfunctions of this repulsive potential. And if you do it this way, it's obvious that this must not necessarily be 1 over r. It can be any potential. You can, in principle, always do that. And so you measure the probability in these, in this Fourier space, if you want, and can connect that to internuclear distance. But then the one-to-one mapping is not there anymore, or it's approximate. Okay, so does it work? Here's the, if you open the chemistry textbook, that's the H2 plus wave function. So the internuclear distance, 1 nucleus sits here, and that's the distribution of the second one, and these are the vibrationally excited states of the H2 plus. And so that was what was in the textbook up to now. Well, this extremely talented experimentalist didn't like these theoretical pictures, so he set off 2 years of very hard work in the laboratory to get the first picture of this wave function. And here it is, done by a derivative of Coulomb explosion imaging. It's a little lengthy to explain how it was actually done, that you also get the energy scale, but I could go into that if you have questions. And what you get is, indeed, you get for each vibrational level, that's an H2 plus, which is created in an ion source. So you bombard your H2 with electrons in an ion source, you cook it up, you make H2 plus ions, which are in all kinds of vibrationally excited states, as you can see here, and then you Coulomb explode it and measure the energy very precisely, and you see indeed the wave function as they are from the chemistry textbook. There is actually a long story about Heisenberg behind here, which I don't have time to go into details, how event for event here the uncertainty principle was taken into account, and there are 2 ways to do it, and that is the mean value of these 2 ways how to do it, which finally agrees very well with the calculation. So that's not beating Heisenberg, it's treating Heisenberg very cleverly, so you can eventually get the wave function. Okay, so these 2, there's one number I just want to draw your attention. I mean, it's trivial, but please remember this is a normal molecule, and the size of a normal molecule is in the range of angstroms, because that's very different from the examples I will show you now. Okay, so that was the experimental intro to convince you that in 3D and in 2D we can actually see wave functions. Coulomb explosion imaging is highly precise. And now we want to use that tool for examining these helium dimers and trimers, which are now non-trivial wave functions in a sense. To understand what happens in the transition when you loosen the bond, here is a deeply bound system, a vibrational distribution, a potential which is so deep that you have 1, 2, 3, 4, 5 vibrational states. And now the question is, what happens to these vibrational states if we decrease the strength of the bond? So we go up. So let's do it. We go up, and you see if you count one after the other, vibrational states gets unbound and disappears. And now we keep going. And there is a situation where we are left with only one vibrational bound state. And the interesting point comes now. What happens if we now keep going? I have to expand the scale that you can see what quantum mechanics does under these circumstances. If you examine the wave, this only one bound wave function now, it has an outer turning point. So a classical particle would roll between this and this point. These are the turning points. Since it's quantum mechanics, you have some kind of tunneling here into the classically forbidden region where the particles have negative kinetic energy. And that is the zero-point motion, and that is the binding energy. And now we reduce that and keep going. And what happens is that the zero-point motion stays approximately the same, because the zero-point motion is related to, you confine it in space, so that's related to the delta P of the uncertainty relationship, so that stays approximately the same. And the system approaches zero. And at the threshold, which is now, something remarkably happens, that the system expands to infinity. At threshold, it really goes to infinity, and slightly below threshold, you get an exponential decay, which, well, decays extremely slowly as you approach threshold. And that is what is called the quantum halo states, because everything which I've colored in yellow here is something where the wave function is actually below has negative energy. All of this is in the tunneling region, and only this small part of the wave function here is actually a normal wave function, which is sitting in a potential like you are used to it. And so the tunneling part by far is bigger than the non-tunneling part of that wave function. And that is, by definition, is called a quantum halo state, and that is realized in many nuclei, for example. Now, the fun thing is that there is one system that is helium-2, the helium dimer, where this strange situation, just by coincidence, is realized. This is now the real interaction potential of two helium atoms, the van der Waals potential between two helium atoms, and you can see it goes down to only 1 milli-electron volt. To be compared to, if you think of a normal molecule, this is a few eV. Here you are only at, because it's van der Waals, at 1 milli-eV. And that is one of the calculations, pretty good calculation. So you see the depth of the potential, and that is the calculated zero-point energy. So is this bound? Well, you have to look at the last digit to see if the difference between the depth of the potential and the zero-point motion, which takes it up here, is positive and negative, or negative. And if you see the numbers, you won't be surprised to hear that there is a 30-year-long dispute which of these numbers actually is bigger. You need a very high accuracy in the calculation of that potential to answer that question. And today we know it's bound. So the zero-point motion is slightly smaller than the depth of the potential, and the difference is here in the last digits. It's around between 100 and 200 nano-electron volts, how this is actually bound. And that it's bound was seen first by Tönnies and Shelkoff some 20 years ago. They detected, in a free-flying helium jet, they detected these helium dimers. Now, that is the potential. Now, how are the predictions for the wave functions? To see the wave functions, you have to completely change scale. So watch this now. We zoom out, and potential is in here, and that is a calculated wave function. So it really, really is not in the pocket of the potential. This thing lives out here, and the expectation value from, that's one of many calculations, the expectation value is 52 angstrom. The potential was at 3 angstrom, this here. So that's a huge, huge thing. You better think of this as being 2 individual helium atoms which are bound by nothing. Well, if they're out there, they have negative energy. Here are the numbers if you are a chemist, that's in kilojoule per mole. And this thing here is now, that is to scale. So they are so far apart that if you would stretch a DNA, you could actually slide a DNA through that dimer. There are 2 calculations in here which differ. The difference between, well, none of these is the latest calculation, but I show them here to illustrate. One of these calculations has retardation in, so the fact that the Coulomb potential from one to the other needs there is a time delay for the Coulomb potential from here to here, and if you put that into the calculation or don't do it, the wave function changes. Okay, so that's what we are after. We want to see that wave function by Coulomb explosion imaging. Before you can do that, you first have to make these dimers. How do you do that? They are bound by only nanoelectron volts. Well, nature helps you. If you press helium gas, if you cool helium gas to some 10 Kelvin, then you press it through a tiny nozzle into vacuum, the gas cools down. If you make it cooler, you get bigger clusters. At this particular conditions we have used, you get about 98% of just non-condensed helium beam. In this are some like 1% of these dimers, and in the range of 1% of trimers and no heavier clusters. Now, to do experiments in only the dimers or only the trimers, to do that, we sent this beam after about ½ a meter. We sent the beam through a narrow slit, and behind the slit, we put a freestanding diffraction grating, which has a grating spacing of 100 nanometers. And now to understand what's happening there, you have to no longer think of this as little balls flying, but consider they have a de Broglie wavelength. They are quantum particles, and they all fly, no matter what their mass is, they all fly with the same velocity. That's how this expansion works. So the difference between a monomer, a helium atom, and the dimer is they have different mass, so the de Broglie wavelength is different. So the diffraction at that grating is different, so the helium atoms show that diffraction a pattern, and the twice as heavy helium dimers, the diffraction is compressed by a factor of 2. And in between are the trimers. So if now you fire your laser in space here, you can do experiments on only the dimers. If you move your laser a little, there is a space where you can meet only the trimers. And here's that this really works. So that's scanning the laser, basically. And you see the helium monomers. You see a space where you have the trimers and the second maximum of the trimers and the helium dimers. And now we can look at the wave function of these species individually. And that's quite a challenge. Here's a paper from 2001 where they claim that this, for quantum chemistry, is really a benchmark. And that was 2001, and it's still true today. I've now shown you the same potential as before, the internuclear distance, and the 1 millieV now is down in the basement here. That is nano EV here, and that is the calculated binding energy from a very popular helium-helium interaction potential. And here are some other calculations, and the most recent one is this here. So what you see is, as time changes, the predictions for the binding energy fluctuate by a factor of 2, which is surprising since this is only 2 atoms, and the binding energy is that uncertain. Okay, so let's look at the wave function. now I've put on a logarithmic scale the potential again, and out here there is basically no force because the van der Waals interaction falls with 1 over r to the 6, which is very fast. So out here the potential is literally 0. There is no force, and if a particle is out here, it's pure tunneling. So everything in here is in the tunneling region. Particles have negative kinetic energy. Now, if you think back of your introductory quantum mechanics course, and all the different theories agree on that point, if you are in the tunneling region of any wave function, the wave function becomes, according to textbooks, very simple. It's proportional to an exponential, decaying exponential, and in the exponent, there are only trivial quantities. There is a mass, heavy particles have a hard time to tunnel. There is h bar, and there is the binding energy. The binding energy is how far below 0 you are. That's the cost you have to pay for tunneling. The punishment, heavy particles and a lot of energy are bad for tunneling, and that's the internuclear distance with which it decays. So that's the good news is, all of these are known quantities. If we can really see that exponential decaying function here, we have measured the binding energy. So that's cheap. You can measure by shooting 10 to the 15 watts per square centimeter laser on it. You can still measure nano electron volts of binding energy by Coulomb explosion imaging. That's a trick. And now here comes the wave function as you get it from Coulomb explosion imaging. And that's on a logarithmic scale. These are real data. And now you can fit it, and you get this here. And we have repeated that experiment several times. We have done it with femtosecond lasers. We have done it with free electron lasers. And from this, you get a feeling how good or how bad your calibrations are. And the current error bar is what's given here, 140 plus minus 10 nanoelectron volts, which is obtained from the reproducibility of this number. The difficulty is to get a calibration for this axis. There are a lot of, and some problems with quantum mechanics that the ionization process itself imparts some momentum, and that slightly influences the Coulomb explosion. And that is from two PhD works from Stefan Zeller and Jörg Vogtsberger. And just to conclude that part, I show you some of the calculations. The best calculation, supposedly, according to the theoreticians, best calculation from 2010 is within our claimed uncertainty, and that are actually the most popular helium interaction potentials. And you see, if you go out, it's wrong by a factor of 10 or so. And okay, that's new data from free electron laser, which agree. Okay, so the summary of this is two helium atoms is really a halo system which lives in the tunnel. What about now adding a third, looking at 3 helium atoms? 3, how do you order 3 particles? You get an equilateral triangle, you explode it, and you can do the same, calculate from the potential energy, which is 1 over the distances. You can calculate your kinetic energy release, so that's what we measure, that's what we are after. So here I plot this kinetic energy, the sum of the energy of the 3 exploding particles. You can convert it to internuclear distance. If you do that on argon, argon 3 is a very stiff equilateral triangle, very well known. You get a peak at a fixed internuclear distance that is an equilateral triangle. Neon is the potential is slightly more attractive, and so it's a little more smeared out here. And so what about the very, very weakly bound? So argon and neon are well known. So what about helium? If the helium-3 would live in this potential pocket here, you would get a peak here. You would go from argon to neon to helium. If it would look like the dimer, you would get a peak here. So how do 3 helium atoms look like? Well, somewhere in between. And the message you get is also 3 heliums are mostly, if you read 20 atomic units, that's about here. That's also mainly in the tunneling region, but not as far out as the dimer. It's very diffuse, it's very broad, it's actually broader than the center, so it's spread. And here theory is doing very well. That's a recent calculation on it. And there is not much dispute. If you replace one of the, that's helium-4. Now in helium you can take off one neutron and see what changes. If you do that in a normal molecule, like let's say H2, if you replace a proton by a D, you change the mass slightly, but the mean internuclear distance doesn't change much. It's just the width of the wave function which changes. What happens here is something dramatic, because in the tunneling formula, the mass enters. So helium-3 is much easier to tunnel out, and that's what you see. If you replace one of the 3 by helium-3, so you increase the size of the thing by about a factor of 2. That's because of tunneling. And what's the shape? Is it a triangle? That's actually a very long story. Well, you might expect that from geometry that's a triangle, but that was a long dispute in the literature. And here's a list. You don't have to read it, just look at the colors. The blue ones claim it's mainly a linear molecule, and the red ones claim it's mainly a triangle, and the black and non-colored ones say it's some random thing. So there's no agreement whatsoever. So here's what you get from experiment. We plot one of the angles. Well, all the 3 angles are the same, so that is the distribution, the probability distribution of that angle, and that's from 1 to 180 degrees. So a linear molecule would give a peak at 180 or 0 respectively. You would get 2 peaks. An equilateral triangle would be 60 degrees, and well enough, neon 3 is an equilateral triangle, and helium now is, well, very broad. So what is it? What does that mean? Is it random? What does random actually mean for a triangle? For a triangle, you can look up mathematics papers. Here's one on random triangle theory. It's undefined what random for a triangle means, but I have a pragmatic proposition what to do. Here's my definition of randomness. Let's take a cloud in the sky and distribute the drops in the sky with a random number generator, which probably is not such a bad approximation. Then you have 2 physics parameters we assume around cloud with equal density of droplets in here, and you have the radius of the sphere, random generated, and then you have an exponential decaying part out here which has an exponential decay. So there are 2 free parameters. Besides that, it's random. And from that random cloud, now with, again, a random generator, we pick 3 droplets, and we do that many times and see what distribution do we get. There's no correlations, nothing built in, just random generator. That's what you get. So, well, to get the answer, you don't need a good theory. I would claim helium-3 is a random cloud with 2 free parameters with which you can change this distribution like in any cloud. Okay, so the answer is it's neither nor, it's an almost random cloud. So it's a first step as you go from the atom, you go to a fluid. That's what you would expect for a fluid. There is no order between the particles if there are no hydrogen bonds or so. And that's what helium really is. 3 is enough to make a random fluid. Okay, so that's the ground state of helium-3. But that is not the only state of helium-3. There is a prediction for a long time now that there is a second state of helium-3, which is, according to theory, an Efimov state. And I have to explain to you what an Efimov state is. Sorry, it's very simple. Remember what I told you about 2 particles. As we decrease the bond from here to here, what happens is before the last bound state disappears, it tunnels to infinity. But there is always only one state at the end, which then disappears. How do we take this scenario now to 3 particles. So here's the deeply bound scenario is very simple. Here's 1 particle. Now we have to expand that to 2 dimensions so I can draw it. So the potential pocket here is now a ring, or in 3D a sphere. If it's a deep pocket, the second particle will sit in this pocket here and have its own attraction, which is here. So that is this. And now if you put a third particle, sure enough, it will reside here, and you get an equilateral triangle. That's neon and argon. That's trivial. And now we make these bonds more loose and go from here to here and look for the 3-particle system and see if also you have just 1, and then it's gone. And the surprise was that in 1970, this by then young Russian nuclear physicist by the name of Vitaly Efimov, he now today is no longer young, but still works and is at Washington State University. He predicted that this transition for 3 particles is very different, because at that threshold, he calculated that there is, instead of, as you hit the threshold, an infinite series of 3-particle states emerges. You are not stuck with 1, but only at that threshold there is an infinite series, almost like a Rydberg series of atoms. And this infinite series of states disappears when you make the potential more attractive. It's very strange. You make the bond stronger and the states disappears. That was his prediction. And if you make it weaker, also there is a limit in which it disappears. And this quantum magic happens only at that threshold. And it's not only that there are infinitely many states, according to his calculation, it's also that these states are enormous in size. The first state has some unknown, but supposedly very big size, and the subsequent infinite number of states scale from state to state, they scale with a factor of 22.7, according to this very simple, actually, calculation. Now that's a very strange prediction, and it's something which happens only in quantum mechanics, that at a threshold you get such a strange phenomenon on gigantic states. And that is what Joe referred to at that quotation I made earlier. This, as he pointed out, is a new kind of how to create, by a trick of quantum mechanics, to create new stable way of making making matter stable. And the fun thing, it's universal. The only thing you have to put into that theory is that the potential has to be short range, and that's it. So it can happen, or predicted to happen, in nuclei, where it was developed for atoms. And today there are also some prediction how you can generalize that for solids. At the beginning, that was only a theoretical prediction, but then 7 years after that prediction, in this paper, it was pointed out that maybe there is one system in the universe where this strange situation, this bond almost zero, is realized to a degree that this Efimov effect already kicks in, and helium would be the example. That was a prediction from 1977. And then there was a long list of theory papers all confirming that helium indeed is the prime candidate for this strange quantum effect. So people start searching for it. But before it was found for helium, there was an unexpected observation of that effect in a kind of indirect way from the cold atoms community. What did they do? Well, they capture their molecules in traps and cool them. And if such a state would occur in a trap, then it's no longer trapped. It loses resonance and it falls out of the trap. You don't see that it falls out. You don't see the state itself, but you see that from your trap the particles disappear. And the beauty of these trap experiments is that the interaction length, the scattering length, you can tune with a magnetic field via Feshbach resonance. So what they did is they changed the magnetic field in these traps and observed a huge increase of the losses from that trap. And that has been confirmed for many species today. And this increase of the loss of the disappearance of atoms from the trap is attributed to this Efimov effect, and you can actually use that to measure the energy. You don't see the wave function, though. That's the way this is plotted usually on this axis here. Binding energy 0 is here, and that is the scattering length. So if you increase the bound, the scattering length gets smaller. If you decrease the bound to 0, the scattering length gets finally to infinity. So that's 1 over the scattering length, and that's the binding strength of this three-body potential. Okay, so helium was predicted to show that, and people searched for it, and this search was concluded unsuccessfully in 2005 with this paper in PIL from the Tönnies group, and they concluded no evidence for any amount of these Efimov states in helium-3. But that was without Coulomb explosion imaging, but just by some tricks with this diffraction grading. So we just tried it again. So again, Coulomb explosion imaging, and the quantity where you would see these enormous things is the kinetic energy release, because the prediction is that these arcs get huge in these Efimov states, so you would get a tiny, tiny kinetic energy release as you explode it if it's there. So now I show you the same data I've shown you before, the kinetic energy of this Coulomb exploding helium-3, but this scale now is logarithmic, and the yellow thing is the ground state, the deeply bound ground state of helium-3, which was what I discussed so far. And the Efimov state, so that is in here, and this huge Efimov state predicted must be somewhere here. So Maxim Konitsky, who is in the audience, did that experiment, and at the beginning we were very disappointed because there's nothing here. This is a logarithmic scale, so you see on 3 orders of magnitude there is nothing where the Efimov state should be. But you should never give up, and Maxim didn't give up, so what experimental parameters do you have? Because for an experimentalist, this is good news. There's nothing means also there is no background, so you can now tweak your experiment, meaning the temperature, the size of the nozzle, which we didn't do, but the pressure of this expansion. By this, you can manipulate how by collisions these trimers are formed, and maybe by a lucky coincidence at some special conditions this Efimov state would be formed. So he worked for several months in the lab, and one day he came with this curve. Well enough, there is a hump at the right position, and he confirmed many times that this is real and no background. And then a few weeks after having this data, Dörner kicked in and presented a calculation for it. And that's a logarithmic scale. So the counts which are here are extremely small. That's why it's so hard to find it. It's like maybe 20 counts or 14 counts per hour in a background of 6,000 per second. So you really have to be sure that you are not measuring nonsense. But by comparison with theory, we know that it's not nonsense. That's a calculation of this Efimov state. That's the ground state, the red one, and the blue and the green one are 2 calculations for this Efimov state from Dörner from Washington. And that are these data on a linear scale, and the green wave function, which fits so well, is actually the best helium-helium interaction potential, which I showed you for the dimer before. Okay, so we are pretty sure this is the Efimov state of helium-3. And, well, you can think about how it's formed. I skipped that, but I show you the size and the structure. Again, you can plot the internuclear distance. Now you have 3 particles, so you pick any of these bonds, and that's the distribution of one of the 3 bonds. That is a ground state here, logarithmic scale, 5 orders of magnitude. Ground state is kind of small compared. The Efimov state is tremendously big, and it also decays exponentially. And the green one for comparison, the green one is the dimer I've shown you before, where I already claimed that it's big. This Efimov state is even bigger. And you can deduct, again, a binding energy and compare that to theory. Now, what's the geometry of this thing? That was not clear for a long time. So in here is the ground state, and out here is my artistic view of the Efimov state. And let's replace it by the real data. Okay, so these are the real data for the Efimov state. And the way this plot is made, these are angstroms here, and there are, for each molecule, there are 3 entries here. And we have sorted them in a way that the axes of this graph are the major and the minor axis of the moments of inertia, of the tensor of inertia. By this way, you make the 3 particles distinguishable. You see, look at their distance from this axis. The one, by definition, is only in the furthest out from the center of mass in this moment of inertia coordinate frame is this one, then the second one is this, and the third one is this. So you see it's by no means an equilateral triangle, but it's a kind of a very long triangle with a short bond and one particle far out. And that's theory in comparison with it, so it does very well. The fact that there is nothing in between here is because in between here, the ground and the Efimov state are identical, so we don't know from the single count which of the states it was. The range of the force, how is this thing bound? The range of the force is this red circle. The size of the hydrogen molecule I've shown you before here, you couldn't see. This is angstrom here, that's 1 angstrom big, so that's a point. And so how is it bound? And how does it look like? One way to think about it is the following. That's again the potential, and everything here is tunneling. So that's on a linear scale now the dimer, so that's the exponential from the dimer on a linear scale. And for this Efimov state now, we have these 3 sides of the triangle, so we can pick the shortest and the longest of these 2 and plot them. And so we can plot the shortest, that's the red one, and the longest. And what you see, the shortest kind of looks similar to the dimer. The longest is very, very different. It's far, far out. So for this Efimov state, so maybe a good picture of this it's a dimer. That's a red curve. And at a huge distance here, it is surrounded by a 3rd particle, which now completely is in the tunnel. And in the mean value, that's a very acute triangle. And that's actually consistent with where this is in the Efimov plot. It's very close to the threshold where it breaks into a dimer and one thing which goes to the continuum. This thing, if you would strengthen the bond, that's strange. If you make the bond tighter, this thing gets kicked out to the continuum, but as the bond is almost 0, it's bound to this orbital. And with this, I'm at the end, and I would just want to mention the people who did the work. Some of them are in the audience. So in the background, always Markus Schöffler and Till Jahnke. The dimer experiment was done by Stefan Zeller, the trimer by Maxim Kunitsky, the trimer ground state by Jörg Vogtsberger, the hydrogen by Lothar Schmidt, and the chiral molecules by Martin Pitzer, and theory support was from several people, but mainly for the dimer and trimer by Dario Bresani for the ground state and Dörner Blume for the Efimov state. And with this, I'm at the end.